Virtualization. An overview. So if an operating system provides the abstraction of a process such that the process can pretend as it's running code that it's the only thing running code on a system and it's the only thing that has access to hardware on a system, but it uses a kernel as the proxy for that hardware or the manager of sorts of that hardware, then virtualization is the layer which effectively provides this abstraction of a guest such that the guest thinks that it's the only operating system using the hardware. Okay, and virtualization is really cool because it gives us the capacity to look at options to slice up hardware for people that want an entire operating system. And this is the whole basis of cloud computing, right? You can take a big beefy server and you can slice it up into chunks, right? Kind of farm it out. Not that it's predetermined chunks, mind you. I don't want you to get confused. But the subdivisioning is effectively that you're not using the full resources unless you pay for something that's like bare metal. Now, we mentioned this Brendan Gregg article, which is really phenomenal, I think, for describing a history of virtualization, at least at AWS, and all the different technologies they've used it, and the different performance characteristics. We went over this chart, which is effectively that the only thing that's going to give you, bare metal performance is actual bare metal. And everything is going to come with some cost. You'll see that the AWS Nitro technology has very, very good near metal performance, whereas things like para-virtualization and up here with early days of Zen and fully emulated, those are effectively not so great for performance, right? Poor performance, or they were optimized for performance. So this is a really great article going through top to bottom and then winding up at Nitro and explaining in really, really short terms about what Nitro is and explaining in really short terms what these other layer types were. And it gives you kind of a history of virtualization. The other use of virtualization is sandboxing for developer experience, right? When you start to use a platform that just puts things in places and there's no layer in between them, you can sometimes wind up in a situation where stuff has been put in a place and something isn't tracking it, right? Or a bunch of mixed versions all wind up somewhere. Python in macOS is a really great example of this, because you'll wind up with like the system Python being invoked, which is like 2.7, I think, and then but tools want more up-to-date Python, whether it's 3.5, 3.7, 3.8, 3.9, etc. And it can be really, really nice if you're developing something to have this nice, clean room of sorts that you can just trash if things go wrong, right? Something isn't installed correctly, we're not put in the right place. Instead of administering it and wasting all my time administering it, you can just blow it away and start over again. And this is sort of the cattle/pet idea, although realistically that analogy isn't so great, because cattle are actually treated with a lot of attention and care when they get sick. But that aside, there's a great Dan Liu article about that, actually. Or maybe it's a Twitter thread. I'll find that as well. Kind of exploring the genesis of that word, or the etymology of that word for this purpose. But the point of the analogy is supposed to be that when it's scrappable experiences, right? So instead of saying, I need to pay full-time a systems administrator to take care of this server, we can just say, hey, blow away the one that we rented and spin up a new one, right? So virtualization layers are cool, but there's all sorts of different types. And Firecracker is what's known as a microvm. And we cloned this project, and then after cloning, we built it using their dev tool, which actually invokes Docker, builds it in Docker because it's building it with Muscle or Musel, I'm not sure how you pronounce it. And then we saw that actually get output on our local directory because it's statically linked. It's a portable binary. All right. So in terms of what this dev tool provides us, where am I? Right. Let's have a look. So they have this TLDR up here, which effectively said we can run devtool build and where to find the binaries. So build effectively is doing a non-release binary, devtool test, and devtool shell. So I think it would be a good idea to try running the tests and also to look at them. And we got kind of a sense of the layout of the crates. So it's a workspace project with several crates. And we're going to sort of just go through and figure this out. And as a reminder, I have never looked at this project before, and I'm not necessarily the best at internals for virtualization. I'm not an expert. So part of the purpose of this is twofold. I want to help teach you how to dive into foreign code bases and pick up information as you go. It doesn't mean that you're going to overnight become an expert, but it does mean that you may wind up with a bit more a bit less fear about diving into unknown places, and hopefully you'll pick up some skills from this. And additionally, maybe you will pick up some things about virtualization in and of itself, because every project has benefits to teaching you little kind of quirks or things that they do. In that same vein, a really good way to learn Rust is to look at how other idiomatic Rust is written. For example, if you go to a language like Python or Haskell or whatever, and you really want to understand how, quote unquote, idiomatic, right, for that more global context or something, code is written, you can start looking at standard libraries. You can start looking at, major projects that are written in it, etc. Now, one project for this, idiomatically, as an aside, that I like to steer people towards is actually to start off first by looking at the Rust standard library. And that's just a good example of, hey, here's some people who directly have touched, the language, maybe not, but they have really, they're tied into the same processes, they're really interested in the language. Here's how they write code. And idioms are not supposed to be about, like the focus of writing idiomatic code is not supposed to be about writing the best code out there, right? Idioms can be really, really specialized too. So idioms for an embedded Rust programmer or an embedded C programmer or whatever are going to potentially and most likely be different than the idioms that a, for example, web developer might use, right? So there are some common things. Clippy, the compiler itself, general peer review if you post your code online, that people will sort of say, oh, well, what are you doing here, right? That's a bit iffy. But I would probably say that focusing too much on idiomatic functionality is a pain. Like it's not worth your time. Writing code that's correct, that is, has relatively acceptable performance, and, is easy to grok, or easier to grok and manipulate and modify, that is truly important, right? And idiomatic code can sort of tie into that, but still, that's not the point. So let's dive into it. Tools, dev tool, test. I want to run the test suite, and I also want to check out, we'll get a sense of what it's running. While it's doing this, so we've already seen that there's a there's a PyTest running. Interesting. So performance test of 10 workers. So there's some Python somewhere in this project. So we can fuddle around here. Sometimes you can use ripgrep to look for specific file types. You could additionally do fud, right, and then do that py. Oh, sorry, I forget that it's not blob. There you go. These are all the py things. So there's a bunch of integration tests, functional, build, performance, security. So what I'm going to do is I'm going to get a list of these directories. So let's pass these through xargs dirname, and then I'm going to sort -u. Okay, so it looks like we've got, I don't know why this, oh, okay, weird. It should be automatically putting me in this when I start a terminal, but in any case. So test frameworks and then statistics. So this integration test for performance, test boot time worked. Functional, performance, security, and style. So what I also want to do is I want to ripgrep for test. How many how many of these are there? Right? Well, these are all the files that have test modules in them. So again, I'm going to go dirname and /u. Cool. So yep, there's a bunch of tests that are actually Rust tests inside of this, as well as these Python tests. So let's maybe go have a go at. I'm curious about the performance tests. So here's the performance ones. Test network TCP throughput, test boot time, test snapshot perf, network latency, process startup time, vsoc throughout, test config, vsoc throughput, version serialization benchmark, and network TCP throughput. Now, one of the things that I personally do is I keep a bunch of different journals and notebooks, whether they're digital, whether they're notes. Like, I think anything that you can put thoughts into and come back to is worth your money, right? As long as you use it and as long as it gives you a sense of organization. For me, part of this process that we'll dive into later that's a bit more particular, reading code comes down to like three things, right? There's three common styles, and I've written about this in the past, and there's an article I did on my blog called "Reading Code is Not Reading Code is Decoding." So, reading code is decoding. Wow, ages ago. And this sort of describes three really common, or actually four really common approaches that all sort of interrelate. So the one that we're doing right now is get the code building early and often and make various changes to steady connections, okay? The other one is you read it like literature. So I've been handed code bases and I've literally opened up a bunch of modules and I'll start going, okay, well, what's this thing and what's that thing? And this appears to be some abstraction, but I don't totally get what it does, and etc. Rewrite the code into a version optimized for legibility. So if code is incredibly confusing to you, sometimes you can take it and, take it apart and put it back together again. I mean, a lot of what we do is kind of, especially for learning purposes, taking things apart, putting them on the bench top, analyzing the components, and then putting them back together, right? Restitching things back together and understanding how the connections in a system work. Really, I know that this might be an unpopular opinion possibly, but I really kind of I'm weird where I look through everything in a systems point of view. And you can look at programs like a big system, right? They have modules, even just functions, whatever, units of something that all are interrelating or stitched together in a particular way, composed in a particular way. And if you're rewriting stuff, you're sort of saying, well, the connections that exist now, they're important, but I don't fully see how, maybe there's layers of indirection, or maybe things are named in an awkward way. I want to better understand that. The last one is puzzling through it the same way that a mathematician would tackle it. And this is sort of the Donald Knuth approach. And all these approaches were sort of gleaned from Peter Sebel's book, Coders at Work. And what I love about that book in particular is not necessarily the conversations about other things, although there are great conversations, but he always manages to ask this one question about how do you read code to every person. But surprisingly, people don't talk a lot about code, right? They don't talk a lot about this process of how do you go about reading code. They just sort of pick it up over time and they don't know how to explain it. I think that these four sort of general approaches are really useful, but all of them can be paired with some sort of note-taking. And I guess as a best practice, maybe what I'll do is I'm going to start some notes. So I think it's really important to get this jar mentality into our head, right? You're never going to fill the jar completely. It's a bit like Zeno's paradox, we talked about in the past. But you want to start with like the really big things first, and then keep filling in as you go. So we understand that there's, from these performance things, that there is a boot action. There's some snapshot functionality. There's the ability to start up a process, so booting the operating system versus booting a process on the operating system. Right. VSOC, right? So we'll go, okay, what's a VSOC? Right. And then test version serialization benchmark. That one's curious. And then these network TCP throughputs, right? Firecracker is predominantly used for, so the AWS landscape of virtualization is that a lot of the older instance types, they use, pretty much they're still using Zen, I believe, and others. I don't think there has been any major plan to port those over to the new Nitro architecture. The new Nitro architecture exists on their specifically selected instance types. And if you want to directly, through a product deal with Firecracker, then you want to touch Fargate or Lambda. And there's some interesting characteristics that we can sort of explore based upon this, right? Like people lament a lot about Lambdas being really slow to boot, right? That have lots of memory access. They request really big amounts of, or they request little minimum amounts of memory, so their boot time is really slow. And I actually might be forgetting this because I don't day-to-day touch serverless stuff a lot. But it'd be really kind of curious to see, well, okay, is there a reason for that in Firecracker? Does Firecracker have any kind of optimizations around that? So really what we're recording here is just like big things that we want to come back to and explore and better understand, and maybe take more notes about, and maybe just say, well, I get it, and I don't really need to record that information. So we'll say boot time, optimizations for boot time of Lambda. Then after we talk about those optimizations, one thing we talked about previously was this focus of virtualization around security, right? If you're running multiple different operating systems all on the same hardware, how do you prevent one of the guest operating systems from being malicious? If you are running virtualization on a local development box and you're just pulling images willy-nilly, how do you prevent a rogue or malicious image from, wreaking absolute havoc on a computer, right? So for example, like, what if you downloaded an image, like what we did previously when we built Firecracker, and it output a file that replaced sudo, right? That always recorded your password and sent a network request up to a common place, and you had no idea that it was doing this, right? So Firecracker claims to have really good security handling with seccomp BPF, and I won't go into what BPF is, and I won't go into seccomp, but I do know that this isn't necessarily a clear concept, so we're going to add it to the list. So let's maybe look at some of these, right? So there's vsoc throughput test config and vsoc throughput. So this is the actual test itself. And we can also Google this a bit. So I'll add a link in the description afterwards of that article. Yeah, we get to have the other fun again of me trying to copy paste stuff in Linux. There. vsoc Linux man page, right? This man7 one is really good. There's also this other one. It has a dice on it. It's like D something. vsoc address family facilitates communication between virtual machines and the hosts they are running on. So this is built-in Linux support for this address family is used by guests, agents, and hypervisor services that need a communications channel that is independent of virtual machine network configuration. Okay, so that's part of the thing that we can add here to our list is like, what's a vsoc, why network TCP throughput, IPC for inter-process communication or inter-guest communication maybe. So send, write, receive, read, listen, bind, connect, common socket things. It is a socket type. So virtualized socket, cool, that's what it stands for. And we can even, let's see if that copy pasted. Getting the hang of this. So, cool, we got that. We don't really need to keep looking at this, but one of the things about Firecracker is that it is, here, I'll show you. It has it in this description, but I want to KVM. Firecracker is a virtual machine monitor that uses the Linux kernel-based virtual machine, okay? KVM. Kernel-based thing, virtual machine. Wikipedia and this other one, this main site. So this is the main site for it, status and features, developing on it or hacking on it. And you'll see it's not funny, it's got a little Red Hat logo on it. And so this is partly what it's driving on. So that's why we saw vsoc, because it kind of unabashedly is running on this thing. And here's an image. So we see that there's the KVM guest. It runs applications. There's the KVM guest kernel, which is file system and block devices and drivers. This is kind of weird because normally the application would be communicating with the kernel, and the kernel would be communicating to the driver, and then the driver would be communicating to the file system and block devices, but that's not important. Now, there's these virtualized CPUs, right? So the kernel here is implemented against these virtualized CPUs. So there's CPU 0 to N, and the virtualized CPU is what has been allotted to the guest, right? This is why if you've ever mucked around with like Kubernetes or whatever, there is some resource limitation. And so guests can also be kind of squeezed in terms of their resources. It's not just a matter of saying, hey, you get this full access to the hardware. You can also say that, no, you actually only get a certain slice of access. And in Linux, there is this idea of C groups in containerization, which we'll talk about in a later video, that is effectively this idea. Then you've got hardware emulation, QEMU. This guy is, I'm not 100% sure what this layer is doing, but effectively this guy's running some stuff on top of this vCPU stuff, and then also running into an IO thread. So only one thread can run QEMU code at any time, QEMU mutex. And generates IO requests to the host on guest behalf and handles events. So this is basically like the guest wants some additional access to a disk, like a real disk. Okay, well, it's going to have to go through this emulated version, and that emulated version is going to run on a single IO thread, and then that is going to directly ask the Linux kernel here, this KVM kernel, which is another layer or hypervisor of sorts, to do file system and block device access and physical drivers. So this is the real non-virtualized version of these drivers. Okay. Then you've got the actual hardware that this KVM kernel is talking to, and it has the real CPUs and it has the real disks. And so, let's see here, is a virtualization module in the Linux kernel that allows the kernel to function as a hypervisor, right? And you see here that a hypervisor is computer software, firmware, or hardware that creates and runs virtual machines. So it is a layer that sits on top of the hardware that provides this sort of guest abstraction. A computer on which a hypervisor runs one or more virtual machines is called a host machine, and each virtual machine is called a guest machine, and we don't need to read the rest, right? One particularly interesting thing that we haven't really talked about yet is like type 1 versus type 2 virtualization, and or different types of hypervisors, right? You can go look at that now. You'll see that. There's type 1 native or bare metal hypervisors, and then type 2 is hosted. I don't want to get into, like it actually has a good point here, which is, the distinction between type 1 and type 2 isn't always clear. For instance, Linux's kernel-based virtual machine and FreeBSD's BIVE are kernel modules, right, that effectively convert the host operating system to a type 1 hypervisor. At the same time, since Linux distributions and FreeBSD are still general-purpose operating systems with applications competing with each other for VM resources, KVM and BIVE can also be categorized as type 2 hypervisors. So that's actually a really good description of the two in a single paragraph, right? And here's an image of it too, right? So we have type 1, OS, hypervisor, hardware. And this one is OS, hypervisor, another OS, hardware, right? So that's hosted, right? Some other operating system is hosting the hypervisor. And KVM is a hybrid example of that. Okay? So, without much further ado, it also gives some examples here of where it's used, but we'll go back to the tests. And there is actually one failed test that happened here. There were a couple that got skipped. There was a test balloon snapshot thing that failed. And these actually might be marked as acceptable fails. So let's go have a look. Test snapshot create full latency failed. All right, sorry. Test snapshot create full latency. Here we are. Okay. So, test scenario, full snapshot create performance measurement. Artifact collection, test images S3 bucket. Now, I know that the emphasis on this program is supposed to be Rust, but I really want to stress that diving into a code base is never ever going to be just one entire language. Now, it could be. All right, I'm not going to rule that out. Sorry. I scratch what I said. Probabilistically, it's more likely that when you go to dive into things, you're going to have to look at stuff that was written in multiple languages. All right. And Python is sort of ubiquitous now as a test harness or a task runner or whatever. So that's an alternative way that a lot of people really like to handle this stuff. And so what it's doing is it's actually building, we can look here, there's an artifact set. So it's doing all this sort of preamble thing, right? It's describing parameters for the guest operating system. So it says testing matrix, guest kernel, Linux 4.14. rootfs is Ubuntu 18.04. The microvm is equipped with 2 vCPUs and 256 out of 512 megabyte RAM. Okay, and multiple microvm sizes must be tested in the async pipeline as a to-do. So somebody wrote this, and we can actually go look at the history here. It says add snapshot create load performance test, signed off by Andre Sandu. Add metric setup and build from snapshot. Add test to sample 3, load, and 3 create latencies. Added some temporary baseline latencies. So this is when it was first created. Create a test context and add builder. So one thing that we haven't seen is there a CI for this. Build RS, third party, specification, security, README, PGP key, maintainers, license, FAQ. What is this? Markdown LRC. Okay. Mail map, git lint, git ignore, tools, test, source for sources, GitHub. There is a CI thing. So what I'm curious about is what CI are they using? And I don't see any kind of status checks on stuff. Here we go. Ah, so they're using build kite. Okay. And this may not be public. Oh, it is. Cool. So build kite is a pretty cool CI I've talked about in the past. What it is they've effectively provide you all the software to run on a host machine and a UI for signing up. It's a bit expensive, but I really like the flexibility that it provides. I only say that it's expensive because I know that some people really just want no cost, right? So we can see that there ought to be somewhere in this thing a build kite pipeline description, but it looks like they might have that actually embedded as part of the UI. You can do that as well. And you see that here when they run AMD, huh? So AMD, 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 AMD. So here's the performance tests, and all these things are passing on these machines. So what is this machine that they're running it on? It's not going to be possible for us to tell. But we can tell that these tests should not be failing. They're not marked as whatever. So some of these things are really a matter of, you know, something failing for us. And let's see what it's actually doing to our hardware as well. You'll see that PyTest is taking 11.7% of the CPU. And, you know, we'll get these nice little pretty graphs and everything, but it's not really important. So the important bit is we have all of these integration tests that are being run. They have nice ways of sort of building up these microvms. I want to go look at microvm builder. So framework builder. And I suspect that what we're going to see out of this is an ability to run the command, the local command. So yeah, there's the Firecracker binary and the jailer binary. And so fc binary init build a fresh microvm. Initialize the microvm with this binary. Build from snapshot. So the snapshot functionality, I'm going to just go out on a limb here and assume that it's fundamentally about actually recording what is there at that moment. And then after that, being able to resume at that particular point in time. If you are familiar with like VMware or whatever back in the day, or even still to the day, it's not like VMware is going anywhere, or VirtualBox or whatever, you'd have this ability that you could spin up a host image, right? And then after you spun up the host image, you were able to, say for example, say, I want to stop here. So you could snapshot everything and it would tarball or whatever the format was, the drives, the state of the CPU, etc. It would basically stash away all the state of the running system, and then you'd be able to come back and it would just resume everything as if nothing had happened at that point. It's a bit like some video game emulators do this, right? They have state snapshot changes, and that's effectively what Snapshot is here, I believe. So let's go find a init microvm, a conf test. A init microvm says it's an auxiliary function for instantiating a microvm and setting it up. Okay, so microvm ID is just a UUID 4, which is guaranteed to be unique. It checks to get the Firecracker and Jailer binary, or actually no, it checks to get one of them, so it gets the Firecracker binaries, and then it asserts that they exist, and then it makes this thing. So where is this guy? Framework microvm. A microvm initializes with a resource path, an FC binary path, etc. A bunch of getters, setters, flushing metrics, get all metrics, append to log data, enable CPU load monitor. Setup. So making some directories. How far? We're at 44%. Spawning. Here we go. Start on microvm as a daemon or in a screen session. This one is interesting, right? So actions, balloon, boot source, describe instance, drive, logger, machine configure. So balloon is interesting. Right. We might go a little bit over today just to sort of explore a bit more. Metrics and MMDS, which we've seen. And delete old screen log if any. Okay. Screen PID, no API, wait create, check log message, serial input, basic config. Shortcut for quickly configuring a microvm. Okay, so this is good. This is basically a default thing. You could call this and it has all these defaults. Memory size of 256. No HT enabled, add root devices enabled, boot args is not, there's none. Using init RD is false by default, and then track 30 pages is false, and then vCPU count is 2, so more than a single core. So what's interesting is we haven't, that spawn one, right? Here, we want to go to the end and see, wait create. Wait for the jailer to create resources needed and Firecracker to create its API socket. We expect the jailer to start within 80 milliseconds. However, we wait for 1 second since we are rechecking the existence of the socket 5 times and leave 0.2 delay between them. This insinuates that there's a relationship between the jailer binary and the microvm itself. So the jailer, I assume, jails Firecracker, and then Firecracker runs within that context of being jailed. And we're still seeing intermittent failures, which I find really interesting, especially since it's running in a container. But it could be that the version of the container we're running is not quite up to par with what we had. I'm not sure. Any case, so before we go, recap. What have we done? We've run the tests. They're still running, but we've noticed failures. We figured out that the project is running with build kite and that the build kite builds actually don't have failures. So it's not that there's just expected failures. We had a look through the Python scripts that instrument a lot of the testing and instrument the binaries to run for testing. And we didn't really dig super deeply into it. We kind of followed a thread with one of the performance ones. Additionally, I think next time when we pick this up, we can start to look at some of these crates. And it's probably a good idea for us to get an idea of, you know, there are different ways to approach digging into this many crates. Way number one, go one at a time and just say alphabetically or whatever, some ordering. Okay, API server, ArchGen, devices, Firecracker, kernel, microHTTP, etc. Or you can go bottom up, which is like trace all the dependencies of something, find all the leaves in the tree or the graph, and then start saying, oh, well, this is just a utility that does foo or something like that, and then build up. Top down, so you start at something like Firecracker or Jailer, and you go out from there, and you say, oh, well, it does this or that, whatever. And then lastly, you've got the hybrid approach, which is both, right? You sort of go both ways, and you find in the middle, right, all the glue logic that stitches these two together, right? This relies on it, but it's really porcelain, right, interface, and this is just utility functionality or core logic. Here's it is in the middle, all being glued together, right? Probably next time we'll dig into showing a bit of both, just so that you get a sense of how that would look. And yeah, hopefully that was fun, and I'll catch you later.